Hello class. Today we're going to get started on our calculus of 1.1 and 1.2, Introduction to Limits. So you might notice that the interface here of this video is a little different. I got the stuff on the bottom. It's because I'm recording my screen here, because we're going to be using Desmos, which is a very strong graphing calculator that will be found online. It's actually a website, desmos.com, and that's what we'll be using throughout this course, since we don't have calculators. But you saw those two videos earlier, and the introduction to calc video that I made, and then the other video that kind of explained limits with the pizza and the disappearing refrigerator. But let's kind of talk about it a little more mathematically. So say we have this blue function here. It's this curve. And remember, we talked about how we want to find the slope of the tangent line. That's a huge concept in calculus, one of our main goals, in fact. But let's think about what's going on. In order for there to be a line, we need 2 points. We can't just have 1 point. We need 2 points to determine the direction that it's going. But notice our tangent line only touches our curve at 1 point, and that's point P. And I have the coordinates here at C, because that's the C. I'm just calling it C. It's an arbitrary x value, comma f of C, the corresponding y value of that point. And we also I also have this other this black line here that goes through point P, but also goes through point Q, and point Q is the coordinates x, f of x. X is just some arbitrary x value. F of x is the corresponding y value. The black one is what we call a secant line, because secant lines cross a curve at 2 points, while a tangent line crosses a curve at 1 point. So our idea of a limit is this. We want to take this secant line, and we want to move point Q closer and closer until we get as close as we can to P without it actually touching P. The reason why we can't actually have it touching P is this. In our function, if you look at our function, the bottom is x minus c. That's our slope, right? It's rise over run. It's our two y values divided by our two x values. If we remember that y2 minus y1 divided by x2 minus x1. As x gets closer to c and as it falls on top of c, it would be some value minus that same value, which would give us a 0 at the bottom, which is why we have to consider limits. We're getting infinitely close to that value, but not actually on that value. So imagine that we have this secant line here, and we're moving point Q closer and closer and closer to P until it reaches P, or infinitely close to P. That is the slope of our tangent line here. It's the limit as x approaches c, so as x gets closer to c, of f of x, our y2 value, minus our y1 value of f of c, divided by our x2 minus x1. So that is essentially our limit. In general terms, our limit is this. The limit as x approaches c of f of x is equal to the number L. And that's what we call it. We call it the number L. And this is actually how it's read. The limit as x approaches c, let me get a little pen to point here. The limit as x approaches c of f of x, some function, is equal to our number L. So let's see what this example is saying. This one is saying the limit as x approaches -1, that our x value is not an arbitrary number anymore, it's a concrete x value, is equal to x squared minus 1 divided by x plus 1, and is equal to -2. Now, we don't have the tools just yet in order to actually solve for this value, but we will obviously get those tools. I'll teach them to you in the next few days here. So hopefully that kind of gives a mathematical perspective of what a limit is. The limit comes from this idea, just to wrap it up again, that we can't have an x distance of 0 in a slope, or else it will be 0 on the bottom, which we can't have. It's kind of like taking a snapshot of something, right? I once had a great professor tell me this kind of what do you call it? Kind of a simile or metaphor, something like that. Imagine you're driving in a car, right? And you're looking at your speedometer, right? The speedometer is the meter that tells you how fast you're going. Going 20 miles per hour, 30 miles per hour. Well, can you ask, how fast am I going right this instant? Can you take a picture of that speedometer or of that car moving? Can you take a picture of a moving car and tell how fast you're going? No, you can't, because you don't have context of 2 points in time to tell you how fast it is going, right? And that's kind of what this tangent line is telling us. It's a snapshot of a picture, but we're able to tell how fast something is going. And that's kind of what a speedometer does. It gives you a snapshot of how fast you're going. Moving on, let's start to investigate some of these limits. Now, there are multiple ways to investigate a limit. One is algebraically, which we will learn at a later point. Another one is through a table, and then another one is just looking at it graphically. And all three of those are useful. Obviously, the table takes some time to set up, so table might not be the most beneficial one or useful one, but it's useful to see it at least once. So, let's investigate the limit as x approaches 2 of 2x plus 5 using this table. So here I have x values that get closer and closer to 2 from the left, and x values that get closer and closer to 2 from the right going down. And actually, I don't want all this to be a distraction down here, so I'll cover it. So let's plug it into a calculator. I know you don't have this graphing calculator, but you have Desmos. You can use it, or you have calculators on your phone, all that stuff. So let's start filling out this table. Okay, so let's start with I'm going to change to green here. Let's start with 1.99. So I'm going to plug that in. And we get 8.98. I'm going to plug in 1.999. And we get 0.998, or sorry, 8.998. You might see a pattern going on here. I'm going to plug in the next one with 4 9s. And we get 8.9998. I'm going to skip 2, and I'm going to go to 2.01. I'm going to plug that in. I get 9.02. Then I'm going to plug in the next one, this 2.001. Get 9.002, and so on. I'm going to plug this one in. And let's see, 9.0002. And as you can see this, as we move from the left closer to 2, it gets closer to, it looks to be 9, right? And as we move from the right to the left, we get closer and closer to 9 as well. So what does it look like the limit is going to be as x approaches 2? Well, it's 9. And in this case, we can actually plug into, the refrigerator is still there in this function because it exists at that point. But the point of a lot of these limits is that that point doesn't actually exist because it would be dividing by 0 at that point, just like our tangent line idea that we had from earlier. Okay. So this directionality that's going on kind of brings up another point, and that is this. We can actually take limits from different directions, and we have mathematical names for these. We have, as you can see, we have the limit as x approaches c, and there's this minus. Well, this minus means we are taking the limit as x approaches c from the left of f of x, and it equals L left. So this is essentially like what we did here. We're taking the limit going from the left. Here, you see the c plus. Well, that means we're taking the limit as x approaches c from the right, just like what we did here, going from right to left as we get infinitely close to this limit. So this is an important concept to understand here, that we are able to and we like to take the limit as things approach as we approach a limit from two different directions. And note, a limit actually only exists if both one-sided limits agree with each other. So say if I'm taking, if I'm taking a left, the limit from the left side, and I take the limit from the right side, and I get two wildly different numbers, then what we say then is that the limit does not exist. And that's possible. Many times a limit won't exist, okay? And this is one of the reasons why, because if they don't match up, or if they don't agree with each other. So let's take a look at this next example. Use a graph to investigate the limit. Use the graph to investigate the limit as x approaches 0 of f of x if f of x is a piecewise function. So remember, a piecewise function is a function composed of two different functions, right? In this case, f of x is equal to x when x is greater than 0, and it's equal to 1 when x is less than 0. So I have this graphed on Desmos. I'm going to go over to Desmos real quickly. And here I have it. This is how you would input it into Desmos. This is the input section, by the way, of Desmos. Piecewise, it's kind of more confusing than other ones. I had to set a certain domain for this. You don't normally have to if it's not a piecewise function. But anyway, let's focus our attention over here. So going from the left, what does it look like my limit will be as x approaches 0? Or in fact, let me create a little slider here. Should have done that before. So as we approach from the left, what is the limit here? And it looks like it's going to be at 0. It looks like it's going to equal 0 right there. So going back to this, the limit as x approaches 0 from the left looks to be 0. Now let's do the same thing, but coming in from the right side. Coming in from the right side, it looks like, well, just staying at a y value of 1, right? So it looks like right there, as we approach infinitely close to 0, our limit is going to be 1 from the right side. So my question to you is this. Does a limit actually exist for f of x here at x equals 0? And in this case, no, it does not, because of this up here. The limit only exists if both one-sided limits agree with each other. In this case, coming from the left, we get 0. Coming in from the right, we get 1. So what we would say here is that the limit does not exist, or just DNE, does not exist. Okay. Now let's use a graph to investigate the limit as x approaches 0 of sine equals x squared. And again, I created a graph here, and that's the graph in green. So let's approach from both sides. As we approach from the left, it looks, as we get closer and closer to 0, as x approaches 0, it looks like we get a y value of 0, right? And as we approach from the right, as x approaches 0 from the right, it looks like we also get 0. So in this case, the limit is 0. So this is kind of an intro to limits. I hope you guys learned something. And we will get more into limits in the next lesson. Have a good day.